Every story has a beginning. Every civilization, every star, every planet, and every living creature can trace its existence back through time. But what happens when we ask about the beginning of the universe itself? It is one of the oldest questions humanity has ever asked. Where did everything come from? Was there a first moment, or has the universe always existed? For thousands of years, philosophers, astronomers, and dreamers searched the night sky, wondering whether the cosmos had a beginning or whether it stretched endlessly into the past. Ancient cultures imagined the universe emerging from chaos, darkness, or divine creation. These stories inspired generations, yet none could be tested by observation or experiment. Modern science approached the mystery differently. Instead of beginning with beliefs, it began with evidence, mathematics, and the remarkable ability to observe the distant universe. The deeper astronomers looked into space, the farther back in time they traveled. Because light takes time to move, every distant galaxy is also a glimpse into the ancient past. A star 1,000 light-years away appears exactly as it was 1,000 years ago. A galaxy a billion light-years away reveals a universe billions of years younger. The universe became more than a place. It became a time machine, allowing humanity to observe its own cosmic history written across the night sky. As telescopes improved, scientists noticed something astonishing. Nearly every distant galaxy was moving away from us, no matter which direction they observed. At first, this seemed impossible. Why would the entire universe appear to be expanding? Was Earth somehow located at the center of everything? The answer was far more extraordinary. It was not galaxies racing through empty space. Space itself was expanding, carrying galaxies apart like dots painted on an inflating balloon. If the universe is expanding today, a simple question naturally follows. What happens if we imagine time flowing backward instead of forward? Running the cosmic clock in reverse reveals galaxies moving closer together. Continue far enough, and every galaxy approaches every other galaxy. The distances separating stars, galaxies, and clusters gradually disappear. The observable universe becomes smaller, denser, and unimaginably hotter. Eventually, mathematics points toward a moment when everything we know appears to have been compressed into an incredibly tiny, energetic state. This idea became known as the Big Bang. Despite its name, it was not an explosion into empty space. It was the rapid expansion of space itself. Imagine winding the clock of the universe backward. Every galaxy moves closer, every star draws inward, and every atom approaches a moment when the universe was smaller, hotter, and denser than anything we can truly imagine. Today, space stretches across billions of light years in every direction. Yet there was a time when all of that vastness was compressed into an unimaginably tiny cosmic beginning. Many people picture the Big Bang as a giant explosion occurring somewhere in empty space. Surprisingly, that image is completely misleading. There was no empty universe waiting for the Big Bang to happen. Space itself did not already exist. The expansion created space as it unfolded. Imagine drawing dots on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot without any single dot becoming the center. Our universe behaves in a remarkably similar way. Every galaxy observes distant galaxies moving away because space itself continues expanding between them. This means the Big Bang did not happen at one location. It happened everywhere at once because every region of space emerged together. Even more extraordinary was the birth of time. According to our current understanding, time did not simply begin ticking inside an already existing universe. Instead, time itself came into existence alongside space. They were born together as parts of a single structure known as space-time. This idea comes directly from Einstein's theory of relativity, where space and time are inseparable, woven together into the fabric of the universe. If space-time itself had a beginning, asking what happened before it becomes surprisingly difficult. It may be like asking what lies north of the North Pole. The question sounds perfectly reasonable, yet it assumes that before has meaning when time itself may not have existed. Some physicists believe the Big Bang truly marks the beginning of time. Others suspect an earlier reality existed, hidden beyond the limits of our current theories. At the moment, no experiment can tell us which possibility is correct, The universe keeps its earliest secrets remarkably well protected. What scientists do know is that the newborn universe was unimaginably hot. Temperatures exceeded anything found inside stars, black holes, or even the most powerful laboratories on Earth. Matter as we know it could not yet exist. At such extreme energies, the familiar particles that make up atoms had not yet formed. Instead, the universe was filled with an intensely energetic sea, where particles continuously appeared, disappeared, and transformed into one another. Every force of nature may also have behaved differently during these first moments, perhaps even existing as a single unified force before separating. The universe had only just begun its extraordinary journey. In less than a trillionth of a second, events would occur that determined the structure of every galaxy, every star, every planet, and ultimately every living creature that would ever exist. To understand how our universe became so vast and remarkably uniform, we must now explore one of the most astonishing events in cosmology, the brief but incredible era known as cosmic inflation. The universe was now less than a trillionth of a trillionth of a trillionth of a second old. Time had barely begun, yet the foundations of everything that would ever exist were already taking shape. At this unimaginable moment, the universe was far smaller than a single atom. It contained no stars, no planets, no galaxies, and not even the particles that make up matter today. Temperatures reached values beyond anything the human mind can truly picture. They were trillions upon trillions of times hotter than the center of our own sun. Under such extreme conditions, the familiar laws of physics begin to blur. Scientists know that nature behaved differently, but exactly how remains one of the greatest mysteries in science. Gravity, electromagnetism, and the nuclear forces may not yet have existed as separate forces. Some physicists believe they were united as one fundamental interaction. If this idea is correct, then the four forces shaping the universe today were once different expressions of a single cosmic force. As the newborn universe expanded, it cooled with astonishing speed. Tiny changes in temperature triggered dramatic transformations throughout the cosmos. Much like water freezing into ice as it cools, the universe underwent a series of phase transitions that permanently changed its structure. Each transition separated one force from another, gradually producing the distinct laws of physics that govern the universe today. These events lasted only tiny fractions of a second, yet they determined the behavior of every star, every galaxy, and every atom that would ever exist. At this stage, matter and energy were almost interchangeable. Particles continuously appeared from pure energy before disappearing again in violent collisions. Countless particle pairs flashed into existence, collided, and vanished almost instantly. The universe resembled a storm of pure energy beyond anything we can recreate on Earth. Remarkably, a tiny imbalance favored matter over antimatter. For every billion pairs that destroyed one another, one extra particle of matter survived. That tiny difference changed everything. Every galaxy, every planet, every mountain, every ocean, and every living creature exists because of those few surviving particles. Had matter and antimatter existed in exactly equal amounts, they would have completely annihilated one another, leaving behind a universe filled only with radiation. Scientists still do not know why nature preferred matter by such a tiny margin. This question remains one of the greatest unsolved mysteries in modern physics. As the universe continued cooling, the conditions became stable enough for entirely new events to unfold, preparing the way for one of the most astonishing episodes in cosmic history. In an instant almost impossible to comprehend, the universe experienced an expansion so rapid that it exceeded anything ordinary intuition can describe. Within an unimaginably small fraction of a second, the universe grew from something far smaller than an atom into a cosmos vastly larger than anyone had once believed possible. This extraordinary event became known as cosmic inflation, a brief but breathtaking moment that shaped the structure of the entire universe and set the stage for everything that followed. For a brief instant after the birth of the universe, something extraordinary happened. Space did not simply expand, it exploded outward at a speed so astonishing that it forever changed the history of the cosmos. This event is known as cosmic inflation, one of the most remarkable ideas ever proposed in modern cosmology. Although it lasted for only a tiny fraction of a second, its effects can still be seen today. Before inflation, the newborn universe may have been unimaginably small, perhaps far smaller than a proton. Yet in an instant beyond comprehension, it expanded by an unimaginable factor. To appreciate how dramatic this was, imagine a grain of sand suddenly growing larger than the entire observable universe in less than the blink of an eye. Nothing inside space was moving faster than light. Instead, space itself was expanding, stretching everything within it as it rapidly grew larger. Einstein's theory of relativity limits how fast objects can travel through space, but it does not prevent space itself from expanding at extraordinary rates. As space-time expanded, tiny quantum fluctuations hidden within the infant universe were stretched across enormous cosmic distances. These microscopic fluctuations were unimaginably small, arising naturally from the strange laws of quantum mechanics during the universe's earliest moments. Normally, such tiny fluctuations would disappear almost instantly. Inflation, however, magnified them into enormous regions of slightly different density. These minute differences became the seeds from which every galaxy, every cluster of galaxies, and every supercluster would eventually form billions of years later. Without inflation, the universe would likely appear completely different. Galaxies might never have formed, stars might never have ignited, and life could have been impossible. Inflation also solved one of cosmology's greatest puzzles. It explained why the universe appears almost perfectly uniform in every direction we observe. No matter where astronomers point their telescopes, the large-scale universe looks remarkably similar, despite regions being separated by billions of light years. Before inflation, scientists struggled to explain this extraordinary uniformity. There simply seemed to be no time for distant regions to exchange information. Inflation provided a beautiful solution. Those distant regions were once incredibly close together before being rapidly stretched apart. Like ink spread evenly across a balloon before it inflates, the universe carried its early uniformity outward as space expanded to enormous scales. Although inflation lasted only an unimaginably brief moment, it determined the large-scale structure of the cosmos that still surrounds us today. Modern satellites have mapped the faint glow left behind from the early universe, revealing tiny temperature variations that match inflation's predictions with remarkable precision. These ancient patterns provide some of the strongest evidence that cosmic inflation truly occurred, preserving a record of events from nearly the beginning of time. From invisible quantum ripples to billions of galaxies scattered across the heavens, the universe's grand architecture may have begun during this breathtaking fraction of a second, proving that the largest structures in existence were born from the smallest fluctuations imaginable. When the brief era of cosmic inflation came to an end, the universe was enormous compared to its original size, but it was still unimaginably hot. The stage was finally set for the birth of matter itself. Energy filled every corner of the young universe. There were no atoms, no stars, and no planets, only an ocean of intense radiation where particles appeared and vanished continuously. According to Einstein's famous equation, E mc2, energy and matter are deeply connected. Under the right conditions, pure energy can transform into particles of matter. In those first moments, collisions between unimaginably energetic particles constantly created new matter from pure energy. The universe became a vast cosmic factory unlike anything seen today. Every newly formed particle was accompanied by its opposite, an antimatter partner with identical mass but opposite electric charge. When matter and antimatter met, they instantly destroyed one another, converting all of their mass back into pure energy in a brilliant flash of radiation. At first, this cosmic battle seemed perfectly balanced. Matter was constantly being created, only to disappear again moments later through annihilation. Then something extraordinary happened. For reasons still unknown, nature developed the tiniest preference for matter over antimatter. For roughly every billion matter and antimatter pairs that annihilated one another, a single extra particle of matter survived the destruction. That tiny imbalance changed the destiny of the entire universe. Every star, every galaxy, every planet, and every living creature exists because of those few surviving particles. Scientists continue searching for the cause of this imbalance. It remains one of the greatest unsolved mysteries in particle physics. As the universe expanded further, its temperature steadily dropped. The violent particle collisions became less frequent, allowing some particles to survive permanently. Among the survivors were quarks, the tiny building blocks that would eventually combine to form protons and neutrons. Powerful nuclear forces quickly bound groups of quarks together, creating the first stable particles capable of forming ordinary matter. These newly formed protons and neutrons became the foundation of everything we see today, from grains of sand to distant galaxies. Although the universe was now filled with matter, it still looked nothing like the cosmos we know. Temperatures remained far too high for atoms to exist. Electrons raced freely through the glowing plasma, unable to attach themselves to atomic nuclei, because energetic radiation constantly tore them apart again. The entire universe resembled a brilliant fog of charged particles, so dense that light itself could travel only a very short distance before scattering. It would take hundreds of thousands of years before the universe cooled enough for the first atoms to form and for light to finally travel freely across space. Those first surviving particles marked one of the greatest turning points in cosmic history. From a tiny excess of matter born in the earliest moments of time, the entire visible universe would eventually emerge, proving that everything around us began with an almost unimaginably small advantage over nothing at all. By now, the universe was several 100,000 years old. It had expanded enormously since the Big Bang, and with every passing moment, it continued to cool. Although matter now existed, the universe was still far from transparent. It remained filled with an intensely hot plasma of electrons, protons, and energetic light. Light was everywhere, but strangely, nothing could truly be seen. Every photon traveled only a tiny distance before colliding with another charged particle. Imagine trying to shine a flashlight through an impossibly thick fog. The light scatters in every direction, preventing it from traveling freely. The early universe behaved in much the same way. It was brilliant beyond imagination, yet completely opaque because photons were trapped within the dense plasma. For nearly 380,000 years, light remained imprisoned inside this glowing cosmic fog. The universe was filled with radiation, but no clear image could ever emerge. Then something extraordinary happened. As expansion continued, temperatures finally dropped below about 3,000 degrees Celsius. This cooling changed everything. Electrons, which had been racing freely through space, finally slowed enough to remain attached to atomic nuclei. For the first time in cosmic history, stable atoms began to form. Hydrogen appeared first, followed by smaller amounts of helium and traces of lithium. This event is known as recombination, although the particles were actually combining for the first time rather than combining again. With most free electrons now locked inside atoms, photons suddenly encountered far fewer obstacles during their journey through space. After hundreds of thousands of years of confinement, light was finally free to travel across the universe without constantly scattering. At that remarkable moment, the universe became transparent. If anyone had been there to witness it, the cosmic fog would have lifted for the very first time. Those ancient photons never stopped traveling. They have continued crossing the universe for more than 13 billion years, carrying a record of the cosmos in its infancy. As the universe expanded, those photons gradually lost energy. Their wavelengths stretched along with space itself, shifting from visible light into microwave radiation. Today, scientists detect this ancient glow as the cosmic microwave background, often called the oldest light in the universe. It is not simply ordinary radiation. It is a snapshot of the universe when it was only 380,000 years old, preserving tiny details from an unimaginably distant past. Modern space observatories have mapped this faint microwave glow with astonishing precision, revealing subtle temperature variations spread across the entire sky. Those tiny variations are far more than random patterns. When the universe became transparent, something extraordinary was set free. Ancient light, trapped since the earliest moments of cosmic history, finally began its endless journey across space. Those first photons traveled in every direction, carrying with them a perfect snapshot of the universe as it existed nearly 380,000 years after the Big Bang. For billions of years, this ancient light crossed the expanding universe without interruption, silently preserving the earliest visible chapter of cosmic history. As space continued expanding, those traveling photons expanded with it. Their wavelengths stretched farther and farther, reducing their energy over immense spans of time. Light that once glowed with the brightness of a blazing furnace gradually shifted beyond visible colors, eventually becoming faint microwave radiation. Today, this ancient glow fills the entire universe. No matter where scientists point their instruments, they detect the same faint background radiation surrounding Earth from every direction. This remarkable discovery became known as the cosmic microwave background, often shortened to the CMB. It is sometimes called the oldest light in the universe. Its existence had been predicted years before it was accidentally discovered, providing one of the strongest confirmations of the Big Bang theory. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, were testing a sensitive antenna when they encountered a mysterious background signal. They checked every possible source of interference. They inspected their equipment, examined nearby radio transmissions, and even removed birds nesting inside the antenna. Yet the strange microwave noise refused to disappear. It arrived equally from every direction, day and night, regardless of where the antenna was pointed. Unknown to them, they had detected the faint afterglow of the Big Bang itself, light that had been traveling through space for nearly 14 billion years. Their accidental discovery became one of the greatest moments in modern astronomy and later earned them the Nobel Prize in Physics. The CMB is astonishingly uniform. Across the entire sky, its temperature is only about 2.7 degrees above absolute zero, making it one of the coldest things in nature. But hidden within that remarkable uniformity are incredibly tiny temperature variations, smaller than 100,000th of a degree. Although almost invisible, these tiny differences change the future of the universe. Regions that were slightly denser contained just enough extra gravity to attract more matter. Over billions of years, those small fluctuations grew into enormous clouds of gas, eventually forming the first stars, galaxies, and galaxy clusters. Space missions such as COBE, WMAP, and Planck mapped these delicate patterns with extraordinary precision, allowing scientists to study the infant universe in unprecedented detail. Today, the cosmic microwave background remains one of humanity's greatest scientific treasures. It is not simply ancient light, it is a photograph of the universe in its earliest visible childhood. Without this extraordinary cosmic snapshot, much of what we know about the origin, age, composition, and evolution of the universe would have remained forever hidden in the darkness before the first stars were born. For millions of years after the first light was released, the universe entered an age unlike any other. It contained no stars, no galaxies, and no visible structures, only endless clouds of hydrogen and helium drifting through the darkness. Astronomers call this period the cosmic dark ages. It was not dark because the universe lacked energy, but because there were no stars yet to illuminate the vastness of space. Although the universe appeared calm, gravity was quietly at work. Tiny regions that contained slightly more matter than their surroundings began pulling in even more material. Over millions of years, these invisible clouds slowly grew larger and denser. Gravity never rushed. It patiently gathered enormous amounts of gas into expanding cosmic structures. As more hydrogen accumulated, the pressure inside these growing clouds steadily increased. Temperatures climbed higher as gravity squeezed the gas closer together. Eventually, the collapsing cloud became so dense that its central temperature reached millions of degrees, creating conditions unlike anything seen since the earliest universe. At that extraordinary moment, hydrogen nuclei began colliding with enough energy to overcome their natural electrical repulsion. For the first time since the Big Bang, nuclear fusion ignited. A new source of light was born, and the first star began shining into the darkness. The cosmic dark ages had finally come to an end. After hundreds of millions of years, the universe witnessed its very first sunrise. These first stars were unlike most stars we see today. Many were hundreds of times more massive than our sun and burned through their fuel at incredible rates. Their brilliant blue-white light flooded the surrounding universe, illuminating enormous regions of space that had remained dark for ages. Inside their blazing cores, these giant stars forged the first heavy elements. Carbon, oxygen, silicon, and many other building blocks of future worlds were created through nuclear fusion. Before these stars existed, the universe contained almost nothing except hydrogen, helium, and tiny traces of lithium. Nearly every heavier element had yet to be born. When the first massive stars reached the end of their lives, they exploded as spectacular supernovae, scattering newly formed elements across the cosmos. Those explosions enriched nearby clouds of gas, providing the raw materials needed for future generations of stars, planets, and eventually life itself. Each new generation of stars contained more heavy elements than the one before, gradually transforming the chemical makeup of the universe. The iron in your blood, the calcium in your bones, and the oxygen you breathe all originated inside ancient stars that lived and died billions of years before Earth existed. In a very real sense, every person is made from recycled stardust, forged in the hearts of stars that illuminated the young universe long before our solar system was born. The birth of the first stars changed the universe forever. Their light ended the cosmic darkness. Their explosions created the ingredients for life, and their gravity began assembling the vast galaxies that would soon dominate the cosmos. When the first stars illuminated the universe, they did not shine alone for long. Gravity continued gathering enormous clouds of gas, slowly assembling structures far greater than individual stars. Tiny variations left behind by the Big Bang had now grown into vast regions rich with matter. Gravity transformed these invisible seeds into the first galaxies. A galaxy is far more than a collection of stars. It is a magnificent cosmic city containing stars, planets, gas, dust, dark matter, and often a supermassive black hole at its heart. The earliest galaxies looked very different from the graceful spirals we admire today. They were small, chaotic, and constantly changing as they grew. Young galaxies frequently collided with one another. These dramatic encounters did not always destroy them. Instead, many merged together to create larger and more complex galaxies. Unlike collisions between solid objects, stars almost never strike each other during these galactic mergers. The immense distances between stars make direct impacts incredibly rare. Instead, gravity reshapes the entire structure. Clouds of gas collapse, new stars ignite, and the galaxies slowly transform into completely new systems. Over billions of years, countless mergers built the giant galaxies that dominate the universe today. Every collision added new stars and fresh supplies of gas. Among these growing galaxies was one that would eventually become our own home, the Milky Way. Scientists believe the Milky Way began as several much smaller galaxies that gradually merged through gravity over billions of years. Even today, our galaxy continues growing. Small neighboring galaxies are still being pulled inward, becoming part of the Milky Way's expanding structure. At the center of nearly every large galaxy lies an astonishing object, a supermassive black hole containing millions or even billions of times the sun's mass. Although invisible, these cosmic giants influence the motion of billions of surrounding stars and may help regulate the evolution of their entire galaxies. Meanwhile, dark matter quietly played an essential role throughout this process. Though invisible, its gravity acted like a vast framework upon which galaxies could form. Without dark matter, ordinary matter alone may never have gathered quickly enough to create the galaxies we observe across the universe today. As galaxies matured, they organized themselves into even larger structures. Groups of galaxies became clusters, while clusters linked together into enormous cosmic filaments. These filaments stretched across hundreds of millions of light years, weaving a breathtaking network known as the cosmic web. Between these glowing strands lay enormous empty regions called cosmic voids, where very few galaxies exist, creating one of the largest patterns in nature. Today, when astronomers map billions of galaxies across the observable universe, they see the same magnificent architecture that began with tiny fluctuations in the first moments after the Big Bang. From nearly featureless clouds of hydrogen to a universe filled with majestic galaxies, gravity patiently transformed simple beginnings into the extraordinary cosmic landscape we see today, preparing the stage for the birth of stars, planets, and eventually life itself. By now, the universe was billions of years old. Countless stars had lived and died, enriching space with the heavy elements needed to create something entirely new, planetary systems. Among the spiral arms of a young galaxy called the Milky Way, an enormous cloud of gas and dust drifted quietly through space for millions of years. This cloud contained the ashes of ancient stars. Every atom of carbon, oxygen, silicon, iron, and calcium had been forged inside suns that no longer existed. Then gravity began its patient work once again. The giant cloud slowly collapsed inward, growing denser as its own weight pulled everything toward the center. As the cloud shrank, it also began spinning faster, just as a figure skater spins more rapidly when pulling in their arms. The rotating cloud gradually flattened into a vast disk stretching billions of kilometers across. At its center, matter continued gathering into an intensely hot sphere. Pressure and temperature increased relentlessly until hydrogen atoms began fusing together. A new star was born, our sun. The newborn sun blazed brilliantly, flooding the surrounding disk with light, heat, and powerful streams of charged particles known as the solar wind. Meanwhile, countless grains of dust inside the disk began sticking together through tiny collisions, forming larger and larger rocky fragments. These fragments became pebbles. Pebbles became boulders. Boulders merged into mountain-sized objects called planetesimals, the first building blocks of planets. Gravity soon took over again. Planetesimals collided repeatedly, growing into enormous bodies that dominated different regions of the young solar system. Closer to the sun, intense heat allowed only rock and metal to survive. These materials eventually formed Mercury, Venus, Earth, and Mars. Farther away, temperatures were much lower. Ice, gas, and frozen compounds accumulated into the giant planets Jupiter, Saturn, Uranus, and Neptune. Not every piece of material became part of a planet. Some remained behind as asteroids, comets, and countless smaller objects still orbiting the sun today. For millions of years, collisions were common. Young planets were constantly struck by enormous bodies, reshaping their surfaces and altering their futures forever. Scientists believe one giant collision changed Earth's history dramatically. A Mars-sized object struck the young Earth, ejecting debris into orbit. That orbiting debris gradually came together under gravity, forming the Moon, Earth's faithful companion that has circled our planet for more than 4 billion years. As the solar system settled into stability, one small rocky planet occupied a very special position, neither too close nor too far from its parent star. That planet was Earth. What began as scattered dust forged inside ancient exploding stars had become a world capable of oceans, continents, atmosphere, and eventually life itself, proving that every chapter of cosmic history had been leading towards something truly extraordinary. About 4.6 billion years ago, our solar system was still a violent place. Young planets collided, asteroids crashed endlessly, and enormous clouds of debris filled the space between newly forming worlds. Among these growing worlds was a small rocky planet orbiting at just the right distance from the sun. This young world would eventually become Earth. At first, Earth looked nothing like the blue planet we know today. Its surface was a blazing ocean of molten rock, heated by constant impacts and radioactive decay. Gigantic asteroids struck the young planet with incredible force, releasing enough energy to melt vast regions of its surface again and again. Deep beneath the molten exterior, heavier elements such as iron and nickel slowly sank toward the center under the pull of gravity. Lighter materials floated upward, forming Earth's rocky mantle and its thin outer crust. This process created the layered structure our planet still possesses today. The sinking iron formed Earth's massive core, where temperatures reached values comparable to the surface of the sun. As the liquid outer core moved around the solid inner core, it generated a powerful magnetic field surrounding the planet. This invisible magnetic shield became one of Earth's greatest protectors, deflecting dangerous charged particles carried by the solar wind. Without this magnetic field, much of Earth's atmosphere might have been stripped away, making life far more difficult or perhaps impossible to sustain. Meanwhile, volcanic eruptions covered the surface with rivers of lava, releasing enormous quantities of gases trapped inside the young planet. These gases gradually formed Earth's first atmosphere, although it contained almost no oxygen and would have been completely unbreathable for humans. Water vapor filled the atmosphere alongside carbon dioxide, methane, nitrogen, and many other gases released from Earth's fiery interior. As the planet slowly cooled, the thick water vapor condensed into clouds stretching across the entire globe. For millions of years, rain fell almost continuously onto the hot surface, filling enormous basins that eventually became the first oceans. Some scientists also believe that icy comets and water-rich asteroids delivered additional water during countless impacts throughout Earth's early history. Gradually, the violent bombardment became less frequent. The surface cooled, stable continents began forming, and the oceans covered much of the planet. For the first time since its birth, Earth offered a relatively stable environment where entirely new chemical processes could begin. No forests covered the land. No fish swam through the oceans. No animals walked across the continents. Yet the essential ingredients for life were finally in place. From a glowing sphere of molten rock to a planet covered with oceans beneath a protective atmosphere, Earth had completed one of the most extraordinary transformations in cosmic history. The next chapter would reveal perhaps the greatest mystery of all, how lifeless matter became living organisms. For billions of years, the universe had been preparing for this extraordinary moment. Stars forged the elements, planets formed from cosmic dust, and Earth slowly became a world capable of supporting something entirely new. Yet one breathtaking question remained unanswered. How does lifeless matter become alive? Even today, scientists continue searching for the complete answer. The origin of life remains one of the greatest mysteries in all of science. What researchers do know is that the young Earth looked nothing like the peaceful world we know today. Volcanoes erupted constantly, lightning flashed across thick skies, and the oceans were rich with simple chemicals. Those ancient oceans became vast natural laboratories. Water, heat, minerals, and energy combined in countless ways over millions of years. Tiny molecules continuously collided, separated, and reformed. Most combinations disappeared almost instantly, but a few proved surprisingly stable. Gradually, more complex molecules began to emerge. Some were capable of storing information, while others helped speed up chemical reactions. Scientists believe that somewhere within this chemical chaos, certain molecules developed the remarkable ability to make copies of themselves. This simple act of self-replication changed everything. Once a molecule could produce copies, natural selection could begin shaping increasingly successful forms. The earliest life was almost certainly microscopic. There were no plants, no animals, and no fish, only tiny single-celled organisms drifting through the ancient oceans. These primitive microbes survived by obtaining energy directly from their surroundings, thriving in environments that would seem hostile to most life today. Some scientists suspect that life may have first appeared near deep-sea hydrothermal vents, where mineral-rich water emerged from cracks in Earth's ocean floor. Others suggest that shallow tidal pools, repeatedly filled and dried by the tides, may have provided ideal conditions for increasingly complex chemistry. There is even a fascinating possibility that some organic molecules arrived from space aboard comets and meteorites, enriching the young Earth with additional ingredients. Whatever the exact path, life appeared surprisingly early in Earth's history. Fossil evidence suggests that microscopic organisms existed more than 3.5 billion years ago. Over immense spans of time, these tiny organisms slowly transformed the planet. Some evolved the ability to capture sunlight through photosynthesis. As they released oxygen into the atmosphere, Earth's environment changed dramatically, paving the way for more complex forms of life. Eventually, simple cells gave rise to more advanced cells. Those cells joined together, forming multicellular organisms that would one day become plants, animals, and ultimately human beings. Every living creature on Earth shares this extraordinary ancestry. From towering redwood forests to whales, eagles, butterflies, and people, all life can trace its history back to those tiny ancient cells. The story of life is not separate from the story of the universe. It is the continuation of it, a remarkable journey that began with the Big Bang and eventually led to conscious beings capable of asking how it all began. For centuries, people believed the universe was eternal and unchanging. The stars seemed fixed, the galaxies appeared permanent, and the cosmos itself looked perfectly still. That comforting picture began to change in the early 20th century, when astronomers built larger telescopes capable of exploring regions far beyond the Milky Way. One of the greatest discoveries came from Edwin Hubble, who carefully measured the light arriving from distant galaxies and noticed something extraordinary. The farther a galaxy was from Earth, the faster it appeared to be moving away. This was not an isolated observation, but a universal pattern repeated across the sky. At first, many scientists found the discovery difficult to believe. Why would nearly every galaxy be moving away from us at the same time? The answer was both simple and astonishing. Galaxies were not flying through empty space like bullets. Instead, space itself was stretching between them. Imagine placing raisins inside a loaf of bread before baking it. As the dough expands, every raisin moves farther away from every other raisin. No raisin sits at the true center of the expansion. From the perspective of each raisin, all the others appear to be moving away. The expanding universe behaves in much the same way. Every galaxy observes distant galaxies receding because the fabric of space itself continues to grow. This discovery transformed cosmology forever. If the universe is expanding today, then it must have been smaller yesterday, and even smaller billions of years ago. Running this expansion backward naturally leads to the Big Bang, the moment when the observable universe occupied an unimaginably tiny, dense state. Einstein's own equations had predicted that the universe could not remain perfectly static. Yet even Einstein initially resisted this conclusion. To preserve the idea of a motionless universe, he introduced an additional mathematical term known as the cosmological constant. When Hubble's observations confirmed that the universe was expanding, Einstein reportedly described adding that term as the greatest mistake of his career. Ironically, decades later, the cosmological constant would return in a completely unexpected way, becoming central to one of the biggest discoveries in modern astronomy. As scientists measured increasingly distant galaxies, they realized they were also looking billions of years into the past. Every powerful telescope became a time machine, revealing different chapters of cosmic history simply by observing objects at greater distances. Today, space observatories such as the James Webb Space Telescope continue pushing that cosmic horizon farther back than ever before, revealing galaxies formed shortly after the Big Bang. The expansion of the universe is not slowing to a stop as once expected. Instead, astonishing evidence suggests that the expansion is actually speeding up. That surprising discovery opened an entirely new mystery. Something invisible appears to be driving the universe apart, leading scientists to propose one of the most mysterious concepts in modern physics: dark energy. The more astronomers explored the universe, the stranger it became. Galaxies behaved as though they contained far more matter than anyone could actually see. At first, scientists assumed their calculations were wrong. Perhaps telescopes were missing faint stars or invisible clouds of gas hidden between the galaxies. But as observations improved, the mystery only grew deeper. Every new measurement pointed toward the same astonishing conclusion. Something invisible was adding enormous amounts of gravity throughout the universe. Yet it produced no light, reflected no light, and absorbed almost none. This mysterious substance became known as dark matter, not because it is black, but because it remains completely invisible to ordinary telescopes. The first clues appeared in the 1930s when astronomer Fritz Zwicky studied massive clusters of galaxies. He discovered that the galaxies were moving far too quickly. According to the visible matter alone, the clusters should have flown apart long ago. Instead, something unseen was holding them together with tremendous gravitational strength. For many years, few scientists accepted Zwicky's remarkable conclusion. The evidence seemed too strange to believe. Then decades later, astronomer Vera Rubin made another extraordinary discovery while studying the rotation of spiral galaxies. According to Newton's laws, stars near the outer edges of a galaxy should orbit much more slowly than stars close to the center. Instead, Rubin found that distant stars were moving almost as fast as those near the galactic core. It was as though an enormous halo of invisible matter surrounded every galaxy, providing additional gravity far beyond what visible stars could explain. The same mysterious pattern appeared everywhere astronomers looked, from individual galaxies to the largest galaxy clusters in the observable universe. Modern observations now suggest that ordinary matter makes up only about 5% of the entire universe. Dark matter accounts for roughly 27%, outweighing all visible stars, planets, gas, and dust by more than 5 times. Without dark matter, gravity would have been far too weak to gather matter into galaxies so quickly after the Big Bang. The magnificent cosmic web stretching across billions of light years may never have formed without its invisible gravitational framework. Yet despite decades of research, scientists still do not know what dark matter actually is. It has never been captured directly, and no laboratory has definitively identified the particle responsible. The universe has revealed the effects of dark matter with overwhelming certainty, but its true nature remains hidden. And even more astonishing, dark matter is not the greatest mystery of the cosmos. An even larger invisible force appears to dominate the universe, pushing space itself to expand ever faster. That mystery is known as dark energy. By the end of the 20th century, astronomers believed they understood the future of the universe. Gravity, they thought, would slowly reduce the expansion until the cosmos eventually began contracting. It seemed like the logical conclusion. Every galaxy attracts every other galaxy through gravity, so the expansion should gradually slow as billions of years pass. To measure this slowdown, 2 independent teams of astronomers began studying distant exploding stars known as Type Ia supernovae. These brilliant explosions act like cosmic lighthouses. Because they shine with nearly the same intrinsic brightness, scientists can accurately measure their distances across billions of light years. By comparing those distances with the speed at which galaxies are moving away, astronomers hoped to determine how quickly the expansion of the universe was slowing. But when the observations were completed, the results shocked the scientific world. Instead of slowing down, the expansion of the universe was speeding up. Every new measurement confirmed the same astonishing conclusion. Galaxies were not merely drifting apart. They were accelerating away from one another across the vastness of space. Something invisible seemed to be overcoming gravity itself, pushing the fabric of the universe outward faster and faster. Scientists gave this mysterious phenomenon a simple name: dark energy. Unlike dark matter, which pulls through gravity, dark energy appears to do the opposite. It causes space itself to expand at an ever-increasing rate. Today, observations suggest that dark energy makes up nearly 68% of the entire universe. When combined with dark matter, this means that everything we can actually see, every galaxy, every star, every planet, every black hole, and every human being represents only about 5% of the cosmos. In other words, 95% of the universe remains invisible and only partially understood. No one knows what dark energy truly is. It has never been observed directly, captured in a laboratory, or explained by any complete physical theory. Some physicists believe it is a property of empty space itself, an energy woven into the very fabric of the vacuum. Others suggest it may point toward entirely new laws of physics waiting to be discovered beyond Einstein's theory of relativity. Modern observatories continue measuring the expansion of the universe with extraordinary precision, searching for clues that might reveal dark energy's true nature. Every new observation raises fresh questions. Is dark energy constant throughout time, or has it changed since the birth of the universe? Will it remain forever, or could it someday disappear? The answer will determine the ultimate fate of the cosmos. Whether the universe expands forever, tears itself apart, or follows a destiny we have not yet imagined depends largely on understanding this invisible force. Dark energy stands as one of the greatest mysteries in modern science. It reminds us that although humanity has learned an astonishing amount about the universe, we still understand only a tiny fraction of the reality surrounding us. Every story has an ending. From the lives of stars to the rise and fall of galaxies, nothing in the universe lasts forever. The greatest question is whether the universe itself will one day come to an end. For centuries, people imagined the cosmos as eternal and unchanging. Today, modern astronomy tells a very different story. The universe has a history and it almost certainly has a future. The challenge is that no one knows exactly what that future will look like. Its fate depends on the mysterious balance between gravity, dark matter, and dark energy. If gravity somehow became stronger than the expansion of space, the universe could eventually stop expanding altogether. Galaxies would slowly halt their retreat. For a brief moment, the universe would reach its greatest size before beginning an unimaginable journey backward. Space itself would start shrinking. Galaxies would move closer together, temperatures would rise, and the entire cosmos would become hotter and denser with every passing billion years. This dramatic scenario is known as the Big Crunch. In theory, the universe would eventually collapse into an extremely dense state, perhaps resembling the conditions that existed at the beginning of time. Some scientists have even suggested that a Big Crunch might trigger another Big Bang, creating an endless cycle of cosmic bursts and rebirths. Yet current observations suggest this outcome is unlikely. Instead of slowing down, the universe continues expanding faster than ever before. If that acceleration continues forever, a very different future awaits. Galaxies will drift farther apart until many disappear beyond the observable universe forever. Billions of years from now, distant galaxies will move away so quickly that their light will never reach future civilizations. The night sky, once filled with countless galaxies, may eventually appear almost empty, leaving only the stars within our own local galactic neighborhood. As trillions of years pass, stars will gradually exhaust their nuclear fuel. New stars will become increasingly rare as the supply of gas slowly disappears. One by one, the brilliant lights of the cosmos will fade. White dwarfs will cool into black dwarfs, neutron stars will grow cold, and even black holes will slowly evaporate through Hawking radiation. This long, quiet future is known as the heat death of the universe, a state where nearly all useful energy has been exhausted. It does not mean the universe disappears. Instead, it becomes unimaginably cold, dark, and silent, with matter spread so thinly that almost nothing ever happens again. There is also a far more dramatic possibility known as the Big Rip. If dark energy grows stronger over time, the expansion of space could become overwhelmingly powerful. In this scenario, galaxies would first be torn apart. After exploring the birth, evolution, and possible future of the universe, one question continues to capture the imagination more than any other. What existed before the Big Bang? At first, the question seems simple. Every event in our everyday lives has a cause, and every beginning appears to follow something that came before it. But the Big Bang presents a unique challenge. According to our current understanding, space and time themselves began with the Big Bang. If time truly began at that moment, then the word before may not have any physical meaning. Without time, there may be no earlier moment to describe. Imagine asking what lies north of the North Pole. The question sounds perfectly reasonable, yet it assumes the existence of a direction that no longer exists. Some physicists believe the same logic applies to time. The Big Bang may represent the earliest moment for which the concept of before simply breaks down. Others, however, are not convinced. They suspect that the Big Bang was not the absolute beginning, but rather the start of the universe we can currently observe. One fascinating proposal suggests that our universe emerged from the collapse of a previous universe in a repeating cycle of cosmic births and deaths. This idea is known as the cyclic universe. According to this model, every cosmic ending may eventually become the beginning of another universe. Another possibility comes from quantum cosmology, where the universe may have appeared naturally through quantum fluctuations in an extremely unusual state. In this picture, the Big Bang was not an explosion from absolute nothingness, but a transition from a quantum state beyond ordinary space and time. Some researchers explore string theory, suggesting that our universe may exist as one membrane floating within a higher dimensional reality. According to these models, collisions between enormous higher dimensional membranes could trigger events resembling the Big Bang. Another remarkable idea is the multiverse. Our universe may be only one bubble among countless universes, each with its own physical laws and cosmic history. If this picture is correct, the Big Bang was not the birth of everything. It was simply the birth of our particular universe. At present, no observation has conclusively confirmed any of these extraordinary ideas. They remain active areas of theoretical research rather than established scientific facts. This is one of the most important lessons in science. A fascinating hypothesis is not the same as proven evidence, no matter how compelling it may sound. Future observatories, gravitational wave detectors, and advances in quantum gravity may one day provide clues about what happened before the earliest moments we can currently observe. Until then, the universe keeps its deepest secret carefully hidden behind a boundary where today's physics can no longer provide definite answers. Perhaps the greatest discovery in the history of science has not yet been made. Somewhere beyond the Big Bang may lie an even deeper reality, waiting for future generations to uncover the next chapter in the story of the cosmos. Our journey began with a simple question: where did the universe come from? Along the way, we discovered that the answer is far more extraordinary than anyone once imagined. We have traveled from the birth of space and time to the first light, from the formation of stars and galaxies to the emergence of planets, oceans, and life itself. We learned that every atom in our bodies was forged inside ancient stars. The calcium in our bones, the oxygen we breathe, and the iron in our blood are all gifts from long-dead suns. The universe is not merely the place where we live. It is the source of everything we are. In a very real sense, every human being is made of stardust. Yet the more we discover, the more mysterious the cosmos becomes. Every great scientific breakthrough reveals new questions waiting beyond the horizon. We now know that ordinary matter, everything we can see with our eyes, represents only about 5% of the universe. The remaining 95% is made of dark matter and dark energy, invisible components whose true nature remains one of science's greatest unsolved mysteries. We have photographed black holes, detected gravitational waves, mapped the oldest light in the universe, and observed galaxies formed billions of years ago. Still, we cannot fully explain how gravity works at the quantum level, what dark matter is made of, or why the expansion of the universe continues to accelerate. Scientists continue building larger telescopes, more powerful particle accelerators, and increasingly sensitive observatories in the hope of uncovering the next great discovery. Every generation inherits questions from those who came before. Every answer becomes the foundation for even greater discoveries waiting in the future. Perhaps one day humanity will finally unite quantum mechanics with Einstein's relativity, revealing a single theory capable of explaining every force in nature. Perhaps we will discover what truly happened before the Big Bang, whether other universes exist, or whether space and time themselves emerge from something even deeper. History has taught us to be careful. Ideas once dismissed as impossible, from black holes to gravitational waves, later became established scientific facts. The universe repeatedly reminds us that reality is under no obligation to match human intuition. Nature is always more creative than our imagination. That is the true beauty of science. It does not promise absolute certainty. Instead, it offers an endless journey driven by curiosity, evidence, and the courage to ask difficult questions. Every child who looks up at the night sky continues the same journey begun by ancient stargazers thousands of years ago, wondering what lies beyond the stars. Perhaps the next revolutionary discovery will come from someone watching this very documentary, inspired to ask a question no one has ever asked before. The story of the universe is still being written. Every observation, every experiment, and every new idea adds another page to a book whose final chapter has not yet been written. And perhaps that is the greatest mystery of all. The universe is not only something we study, it is the story we are part of, the home that created us, and the greatest adventure humanity will ever explore.